Scientific inquiry, processes, and social perspective. Scientific inquiry, processes, and social perspectives. We'll summarize them. Obviously, this is a tremendously large topic, so we'll just hit the high points. And then we'll have a selection of practice questions with answers. Scientific inquiry, processes, and social perspective summary. Let's start with the process of scientific inquiry. There are many different ones, but here's a representative one. Make an observation that is objective and may be duplicated by other scientists. Right here. You don't want to do things that you're the only person who knows what to do. Gather and evaluate available info about the observation from research or talking with other scientists or researchers. Make an educated guess or a hypothesis, really mean the same thing, to explain the cause of the observation, and it must be testable. There must be an experiment you can do to prove it either false or true. Conduct an experiment to test the hypothesis, analyze the data, and report if the hypothesis was supported, and actually report if it wasn't. That's just as important. Share the data with others, and then make new predictions based on the data analysis and conclusions. There are two key definitions in science that don't quite match what you'd use in everyday conversation. That's going to be theory and law. A theory explains why many types of physical phenomena occur and has been repeatedly tested by many researchers and found to be valid. A theory is not just saying, you know what, I theorize that maybe the sun won't come up tomorrow. That's not a theory, that's just silliness. Now, a law also describes physical phenomena and cause and effect relationships. If something happens, then something else will happen. It makes no claim as to why they behave as they do. That's the province of a theory. Like a theory, it has been repeatedly tested and found to be valid. When you design an experiment, you have to design it such that it is carried out without bias towards proving your hypothesis. No matter how elegant that hypothesis may be, if the experiment shows it is false, then a new one is required. A new hypothesis, that is. Once the problem is identified and you have your hypothesis or educated guess, you can design the experiment using prior research as a guide. The experiment should vary only one variable at a time to ensure that the result depends on that one variable. All the other quantities should remain the same. The control variables, they don't change. The independent variable is the one that is altered. The dependent variable occurs based on the independent one. This first paragraph is so important, it's been repeated here. Now, when you analyze your data, analyze it without bias towards your expected result. Let the data speak for themselves. Share the data with other experimenters. If they cannot reproduce the experiment and the results, then it cannot be used to support hypotheses until this is corrected. Scientific knowledge is based on questions that can be answered by experiment, detailed observations, or calculations. This knowledge should lead to models, such as theories and laws, that are then used to make predictions about related phenomena that are not observed yet. If the predictions fail, then the models must be modified to fit the new results. The best models unify different previously separate topics, like electromagnetic theory, that combine electricity and magnetism. Scientific knowledge is always subject to change, as more complete experiments or observations are made, as Einstein's special theory of relativity modified Newton's three laws for objects moving near the speed of light. Didn't get rid of Newton's three laws, it just modified them. And now, a quick tour through physics principles and historical figures. Starting in ancient times, we have Aristotle, who stated you could observe physical phenomena, and that can lead to explanations of why, how they occur. Kind of the foundation of the scientific method all the way back then. Archimedes, who worked with statics with the lever, and hydrostatics, the buoyancy force. Shenhua, the magnetic compass needle. 17th century, so we've jumped ahead a few centuries. Copernicus, the heliocentric model of the solar system, where the sun is at the center of the solar system. Galileo, astronomy, more experimental method, and the telescope. Hooke, discovery of the cell, actually the naming of the cell. Worked on gravity, elasticity, which is Hooke's law, F is equal to minus kx. Newton, of course, the three laws of motion, universal gravitation, optics, calculus, writing of Principia that covered all of mechanics at the time. 19th century. Young, the double slit experiment that showed that light acted as a wave. Dalton, atomic theory. All substances are made up of indivisible atoms. All atoms of a substance are identical. Faraday, one of the most brilliant experimenters of all time, showed electromagnetic induction and used an elementary field theory to explain the action at a distance that was started all the way back with Newton. And the same field theory concepts were later used in the 20th century for quantum physics. Maxwell, who put the theory of electromagnetism on a very solid mathematical front. For Maxwell's equations, talked about the nature of light, and he consolidated a lot of work done by other physicists who were working in electricity and magnetism. James Joule, Watt, thermodynamics, steam engines. At the end of the 19th century, many people thought physics had reached the peak. There was nothing new to be discovered. And then came the 20th century. We have Einstein, of course, with the special theory of relativity, the photoelectric effect, which is where he won his Nobel Prize for the photoelectric effect, and the general theory of relativity. Max Planck, who kicked off quantum physics by studying blackbody radiation. Marie Curie, Henri Becquerel, worked with radioactivity. Then Thomson, Millikan, and Fletcher, the electron discovery and the measurement of electron charge. Schrödinger and Heisenberg, two of the big names in quantum mechanics, but there are just so many people working on that in the 20th century. Lisa Meitner, very heavy into nuclear physics. Then Gell-Mann, Glashow, Weinberg, Tominaga, Feynman, Salam, Kobayashi, Higgs, and so many more doing particle physics. Let's now look at some key chemistry principles and historical figures throughout the ages. Starting in the 17th century, we had Boyle, who created the gas law, stating that the pressure of an ideal gas is inversely proportional to its volume if it has a constant temperature. In the 18th century, we had Lavoisier, had the law of the conservation of mass, and then Coulomb. Coulomb's law states that like charges repel and opposite charges attract. In the 19th century, Avogadro, of Avogadro's number fame, discovered that the number of molecules in a gram-mole sample of a pure substance is 6.02 times 10 to the 23rd. Dalton, atomic theory. All substances are made up of indivisible atoms, can't be split into anything further, no constituents inside the atom. All atoms of a substance are identical. Gay-Lussac, water is 2 parts hydrogen and 1 part oxygen. Mendeleev created the periodic table. Kelvin came up with the concept of absolute zero. Boltzmann, the distribution of molecular velocities in the gas phase. Arrhenius developed the ion theory to explain conductivity in electrolytes. And then Le Chatelier. His principle explains response of dynamic chemical equilibria to external stresses. Then in the 20th century, we had Thomson, Millikan, and Fletcher, and of course all their assistants, worked on the discovery of the electron and the measurement of the electron charge, which is the fundamental charge on anything. Can't get anything smaller until you start talking about quarks and nuclear physics, but we're not going to worry about that now. Bohr, the energy levels of electrons are discrete. Electrons revolve in stable orbits around the nucleus, but can jump from one level to another. Rutherford, nearly the total mass of an atom is concentrated in the nucleus, and then Lewis came up with the electron pair concept of acids and bases. The source for this topic, which is Biology Principles and Historical Figures, is this website right here. Below, it is organized roughly by date, which also correlates with the principles which each scientist helped launch or explore. 16th century, Andreas Vesalius founded modern anatomy, overthrowing misconceptions about the body that had persisted for over 1,000 years. 17th century, Robert Hooke discovered cells and wrote one of the most significant books in scientific history, Micrographia, revealing the microscopic world for the first time. Antony von Leeuwenhoek, the father of microbiology, he used remarkable self-made lenses to discover single-celled animals and plants, bacteria, and spermatozoa. 17th century continued. William Harvey explained blood circulation for the first time, showing there is a complete circuit beginning and ending in the heart. 18th century, Carolus Linnaeus organized our view of the natural world with the two-part naming system that we use to classify all life forms. Named and classified about 13,000 life forms, broke with tradition by classifying humans in the same way as other life forms. 19th century, Theodor Schwann established that the cell is the basic unit of all living things. His classification of cells is the foundation of modern histology, discovered the enzyme pepsin, identified the role that microorganisms play in alcohol fermentation. 19th century continued. Gregor Mendel founded the science of genetics, identified many of the rules of heredity, identified recessive and dominant traits, and that traits are passed from parents to offspring in a mathematically predictable way. Charles Darwin authored one of the most famous books in history on the origin of species, in which he described and provided evidence for the theory of evolution by natural selection. Alfred R. Wallace independently formulated the theory of evolution by natural selection, was one of the first biologists to express concern about the effects that human activities were having on the natural world. Louis Pasteur, the father of modern microbiology, transformed chemistry and biology with his discovery of mirror image molecules, discovered anaerobic bacteria, established the germ theory of disease, invented food preservation by pasteurization. 20th century, Maurice Wilkins initiated the experimental research into DNA that culminated in Watson and Crick's discovery of its structure in 1953. Crystallized DNA and obtained the best quality X-ray images of DNA seen at that time, indicating that DNA molecules were helical. Rosalind Franklin provided much of the experimental data used to establish the structure of DNA, discovered that DNA can exist in two forms. Francis Crick and James Watson, co-discoverer of DNA's structure and replication mechanism, established the sequence hypothesis and the central dogma, discovered that DNA uses a triplet code to control the formation of proteins from amino acids. Ronald Fisher invented experimental design, devised the statistical concept of variance, unified evolution by natural selection with Mendel's rules of inheritance, so defining the new field of population genetics. 20th century continued. Stephen Jay Gould devised the theory of punctuated equilibrium, which proposes that evolution consists of long periods of stability broken by shorter periods of rapid change. An award-winning author and popularizer of science. Barbara McClintock, groundbreaking genetics, showed that genes switch the physical traits of an organism on or off. Discovered chromosomal crossover, which increases genetic variation in species. Discovered transposition, that genes can move about within chromosomes. Linus Pauling, maverick giant of chemistry, formulated valence bond theory and electronegativity, founded the fields of quantum chemistry, molecular biology, and molecular genetics, discovered the alpha helix structure of proteins, and proved that sickle cell anemia is a molecular disease. Carl Woese discovered a third basic form of life, the archaea, redrew the tree of life, revolutionized biology using genetic analysis, allowing all forms of life to be included in the study of evolution. Rachel Carson, a founder of 20th century environmentalism. Her book, Silent Spring, led to a reappraisal of the effect of chemicals such as DDT on the environment, leading to bans and heavy restrictions. Data organization and presentation. Data should be collected in a very organized fashion and should never be removed if it is not believed to be correct. For example, if you take several pages of data and say, wait, this is wrong, don't throw it out, because you may do a later analysis that showed either an unexpected event has occurred and there's some new physics, or you made a mistake and the data really were good. So save the data, everything you take. Calculations, of course, should be complete and accurate. Raw and analyzed data should be presented in several different ways. Tables is a good way to show it, charts is good, and sometimes graphs tell a better story. And the whole point there is so that readers who are very busy doing other work can clearly see what you're up to. Also, analyze your results quickly, however, very carefully. So that's a tough thing to figure which you should do, which is more important. But you have to do it carefully, and you want other groups to examine and reproduce the data, so you don't want to wait too long. Units are very important in physics or in any science, so we can all communicate with the same quantities. And there are 7 base units in the International System Units, SI, and that's a couple French words which I'm not even going to try and pronounce, but we will abbreviate it SI. So we have meters for length, kilograms for mass, seconds for time, amperes for current, Kelvin for degrees, mole, which is your amount of substance, and candela, which is light intensity. And those are our base units. Now, physicists and chemists don't always use meters, for example, or kilograms, depending on what kind of work they're doing. For example, when you're doing optics, you'll talk in terms of nanometers, and a nanometer is 10 to the minus 9th meter, because those are the wavelengths of visible light, several hundred nanometers. But the base unit is still meters. Then you have derived units. Those are a combination of the base units, such as velocity, which is meters per second, force, which is kilogram meters per second squared, which is then given its own unit, newtons. Dimensional analysis is a very powerful tool when you're doing calculations. It will convert less familiar units, and over here I took probably one of the more unfamiliar units, a furlong per fortnight, and that's actually a velocity. Furlong is an Old English measurement for length, and fortnight is 2 weeks. So we want to convert it into SI units typically. So we have a sequence of unit conversion factors. These are unit conversion factors. Each one of them is equal to the number 1. So you can multiply whatever you want by 1 and you still get the same thing. For example, 1 day is always going to be 24 hours. So you divide those, you get 1. You then line it up so you start canceling off the terms you don't want. So there goes furlong. Here goes fortnight. What's next here? I have days here. There go days. And then I go hours. And what am I left with? Meters per second. So it's 1.663 times 10 to the minus 4th meters per second. We're going to talk about sig figs next. This term here is the only one we have to worry about. That has 4 significant figures. So does our answer. This is exact. There are 3,600 seconds in an hour. I mean, point something, something, something. But that's going to be exact to as many places as we want. There's 24 hours in a day. So those are infinite significant figures there. Scientific notation and unit conversion. Scientific notation expresses numbers as a base, normally an integer, followed by a decimal and more integers to the right of the decimal. If you use engineering notation, they have 2 integers to the left of the decimal. And you times that by a power of 10. Here's 10 to the 5th. One of the advantages of scientific notation is it uniquely specifies how many significant figures, which we'll do on the next slide, are in the measurement. All the numbers shown in scientific notation are significant. So in our example up here, the amount of significant figures is 6. This is a significant figure here because the person thought enough to write it there. Unit conversion, again, very similar to dimensional analysis. That's where you use a ratio, again, equal to 1, to convert a measurement to a different unit. So I have 1,000 centimeters. 1 meter has 100 centimeters in it, so 1,000 centimeters is 10 meters. Significant figures, which we've talked about for the last couple of slides, include definite values that you're positive you measured according to your instrument. For example, a meter stick, any of the little tick marks on it, those are definite values. And then one approximate value, which will be the last digit of your significant figures. And then some rules. Non-zero digits and zeros that are located between non-zero digits, so if you have a 4, 0, 5, those are all significant. Zeros to the left of all non-zero digits are not significant. So if you have a number like this, these are not significant. Zeros to the right of all non-zero digits are significant if there is a decimal point either before or after the zeros. So if you have something like this, 0 will be significant if you have a decimal here, even if you don't have anything after that. You very rarely see that, but that would show that you have 3 significant figures. Or if you have this, okay, let's see, this will be significant, but that's not that case. If we have this, 3470, and I have a decimal here, this will be significant because of this decimal place. What happens when we add numbers or divide them? What happens to the significant figures? For example, if you're taking the area of something and one measurement is out to the, you have 3 sig figs and the other one is out to 5 sig figs, what can your answer be when you multiply them? Well, here's our general discussion here of what a sig fig is. Then if you multiply or divide numbers, they will have the same number of significant figures as the number with the least number of significant figures. So if one has 2 significant figures and the other has 10, your answer can only have 2. When you add or subtract numbers, you can have significant figures up to the rightmost column where all the numbers have a significant figure. So if you're adding, let's see, 4200, those zeros are not significant. There's no decimal to the right. And we add to it 121. Well, when you do math, you get this. But in significant figures, these two don't count. So you would round them away. If it was greater than 50, you'd increase this number. So in this case, your answer would be 4300. You're not allowed to use these. Example 1. How many significant figures do the following numbers have? Explain your answers. Start 3.1415. 0.228, 0.022, 56, 5.60, 50.4, and 5,000. For all of these numbers, we're going to use this fact. Non-zero digits are always significant, right? So that's 1 through 9. And in addition, for this number, 3.1415, there is no addition. Those are all significant digits. Let's look at this number. That has 3 because zeros to the left of all non-zero digits, okay, here's your non-zero digits, and the zeros that are to the left of that, those are not significant. So we have 3. This number here, again, we have the non-zero digits are always significant, and zeros to the left of all non-zero digits are not significant. So this is not significant, neither is this. So our answer is 2. And finally, 560, we have non-zero digits are always significant, so there's 2 of them. And then zeros to the right of all non-zero digits are significant if there is a decimal point either before or after the zeros. That doesn't exist. There's no decimal point there. So the 0 is not significant. For these numbers, we have 2 significant digits here, the 5 and 6, because they are non-zero. And this time the 0 is significant because it is to the right of 5 and 6. And there's a decimal point either before or after the zeros. In this case, it's before. So the number of significant figures is 3. This one, 5 and 4 are significant again, and so is the 0. Because zeros located between non-zero digits are always significant. And finally, a large number, 5,000, but it only has 1 significant figure because the zeros there are to the right of the 5, and there's no decimal point anywhere, so there's only 1 significant figure. Example 2. How many significant figures do the results of the following calculations have? Explain your answers. We have 320 times 14, 19 divided by 6.13, 1,000 times 314, 3.14, 62.5 plus 31, 1,280 plus 12, and 97.6 minus 0.422. Example 2. This time we'll cover multiplication and division. The rule is multiplying and dividing numbers will have the same number of significant figures as the number with the least number of significant figures. Let's look at the first one. 2 sig figs, 2 sig figs. You multiply them together, you get 4,480. But we have to round that to 4,500 because both 320 and 14 only have 2 significant figures, so the product can only have 2 significant figures. 19 divided by 6.13. 2 sig figs there, and 6.13 has 3. So you multiply them out, you divide them, and you get 3.099510, and then a whole bunch of numbers after that. But round it off to 3.1 because 19 only has 2 significant figures. Finally on this slide, 1,000 times 3.14. Well, you get 3,140, but this one you really have to take drastic action. You round that off to 3,000 because 1,000 only has 1 significant figure. Finally, addition and subtraction. The rule is the result of adding or subtracting numbers will have significant figures up to the rightmost column where all the numbers have a significant figure. So let's start with 62.5 and 31. Here's a significant figure in the tenths place. 31 has a significant figure in the units place. So you add them and you get 93.5. But you need to round that to 94 because the units column for 31 is the last place where all the numbers have a significant figure. Second, 1280 plus 12. Well, that's 1292, but you have to round it to 1290 as the tens column for 1280, it's right over here, is the last place where all the numbers have a significant figure. So that's the 9 over here. And finally, 97.6 minus 0.422. Here's the last significant figure. That's in the tenths place. And this is in the thousandths place, but we're limited to the tenths place. Add the two numbers, then round it to the tenths place, which would be 97.2. As the tenths column for 97.6 is the last place where all the numbers have a significant figure. There's another concept, which is propagation of uncertainty, or error. When data are collected, there's an uncertainty associated with each measurement due to the device you're using. This uncertainty will get greater, and the other word for that is propagates, when the data are used in calculations. So let's say we're trying to find R, where it's the sum of two different measurements. You have an uncertainty associated with each one of these, kind of like an error, and we're going to call that sigma x and sigma y, to find our new uncertainty, because there's uncertainty in both of these. This is the equation. It's the square root of the square of each uncertainty. What if you have an equation that is a constant times x plus or minus another constant times y? This time, our propagation equation is this right here. And notice how we've added in the constant within the parentheses, so that gets squared along with the uncertainty. It's also an absolute value. So whether this is minus or plus, you get the same propagation formula. There are more complex calculations when you multiply and divide and have power functions, but we're not going to cover that here. You can look those up on your own if you'd like. We're just taking the very simple case here. Sources of error. Measurements are not perfect. Sources of error give rise to uncertainties in your various measurements. Now, procedural errors are not valid sources of error. If you try and say, hey, we did the experiment, but maybe the numbers are off because we didn't follow directions, or we used the wrong equipment, or we were sleeping, that's not good. You have to repeat the experiment with the correct process and not mistakes like that. There are two types of errors that are valid to be reported and discussed. You have systematic errors, and they're due to the difficulty of using a measuring tool or improperly calibrated instruments. This affects the accuracy of the measurement. How close the measurement comes to a generally accepted value, that's affected by systematic errors. And what we're going to do here is draw a dartboard. And let's say you want to get right in the middle, and the darts are like this. Very close to each other, okay? but they're not in the middle. So you would say that's not very accurate. Something's wrong there. There's something wrong with the way you're throwing, and if you adjust for it, you'll get a very nice pattern right in the middle. Random errors are caused by unpredictable changes in the measuring instrument or the environment. So if there's wind blowing here where you're throwing the darts, maybe your pattern would be something like this. Okay, that's a little tougher to deal with. The precision, which is how close multiple measurements of the same quantity are to each other, is affected by random errors. So in this case, you're not accurate, but you're very precise. They're all in the same area. This case here, the second one, he's very accurate, but these two are way far away from it, so you're not very precise. So precise would be this, and accurate could be, well, let's put another couple in here just to make it more accurate. You got 3 there, but you also have some out here. You're accurate, but not very precise. Lab techniques and safety. Labs are fun, they're great, they're educational, but we have to make sure nobody gets hurt. So the way to prevent that is having a written procedure for proper lab techniques and safety procedures. It should be in every lab and be read and understood by all people who work there. And here's a list of different things that should be in your safety and techniques document, and it's certainly not complete. You can certainly add other ones. Proper supervision at all times is required, and if anybody gets sick or hurt, report it immediately to the instructor. Don't judge how sick or injured you are, report it to the instructor, and that does include paper cuts. Personal apparel should be appropriate and protect personnel from potential dangers. Dangling jewelry and headphones are prohibited. Lab equipment should be well maintained and checked frequently. Electrical safety is paramount. Electricity can be very dangerous. Safety equipment such as fume hoods, fire extinguishers and blankets, eye wash and shower stations, and first aid kits should be present as required. And there's more. The lab procedure should be discussed ahead of time so all students know their role. Lab equipment should be taken from its safe storage spot and set up in accordance with the manufacturer's instructions. Don't make it up. If you don't know how to use it, read the instructions. Only plug in equipment with the permission of the instructor after it's been inspected. The instructor should demonstrate the procedure before any students try it. Any deviation from the procedure, for example, if the students come up with what they think is a more clever way of doing it, that's fantastic, but the instructor has to approve it. And then, of course, when you're done, clean up your table. Return all equipment to their storage. Science and technology have brought many benefits and certainly many risks to society and the environment. Sometimes both arise from the same technology. For example, quickly, the automobile. Very handy in getting people to go different places. And on the other hand, many people have been injured and died in auto accidents. So decisions on the trade-offs between the benefits and risks of all technology and science have to be constantly made. Let's look at some big hitters here. Nanotechnology. That is applications that include repairing damaged human tissue, improving the efficiency of solar energy production, and delivering drugs to certain cells. Chemistry shows how 2 drugs interact with one another inside the human body, and it plays a vital role in pharmacology and the synthesis of different pharmaceuticals or drugs. Now, here's a downside. Acid rain happens due to a chemical reaction that occurs when compounds such as sulfur dioxide and nitrogen oxides are released into the air via various manufacturing processes. Continuing our impacts. Medical imaging. Nuclear magnetic resonance happens when the nuclei of atoms within a body begin vibrating when under the influence of radio waves. That's a technique used in the medical field to detect tumors in soft tissues that X-rays can't find. X-rays are good on bone, but not on soft tissues. Air pollution occurs when particulates such as harmful gases or biological molecules are released into the atmosphere. We have water pollution when foreign objects and chemicals enter the aquatic ecosystem. Then, of course, there's the greenhouse effect, which a lot of people talk about. That's the process where radiation from the Earth's atmosphere warms its surface to a temperature above what it normally would be. The good part about that is we're warm. The bad part about it is when we get too warm, that can lead to global warming and other negative things. Halogen radicals that are released into the atmosphere act as a catalyst in the breakdown of ozone. and that can cause the ozone layer depletion. That was a big deal a couple decades ago, so aerosols, certain types of aerosols are banned. Chemical recycling involves chemically reducing a polymer to its original monomer so it can be processed and made into new plastic materials and go back into successful and positive applications of technology. Specifically, let's talk about energy. The generation of usable energy in great quantities for society was a major achievement of the 19th and 20th centuries. But again, it has issues. First, let's classify energy resources as renewable, hydropower, geothermal, biomass, wind and solar. That means they should last forever. And non-renewable, oil, gas, coal, and uranium, which eventually will run out, although hopefully hundreds, thousands of years into the future. All have an impact on the environment in different amounts. Hydropower, very clean, but in some cases, and this is an understatement, communities are moved or destroyed to make way for a dam. Wind and solar are mostly clean, but both are not consistently available. Burning coal, oil, and gas causes air pollution and increased levels of CO2 in the atmosphere, but are very reliable and efficient. And then the transportation of fuels can be risky, and the waste from each process needs to be managed. Chemistry affects your daily life. Let's start with water purification. That's where bad, undesired compounds and contaminants are removed from water through various chemical processes such as water chlorination, ozonation, and chemical neutralization. Soaps are a salt composed of fatty acids. They are able to clean due to their molecular structure. It allows them to emulsify or disperse water-insoluble materials like dirt and oil so it can be removed from your body or from anything you're trying to clean. Plastics, from the movie The Graduate. They're created by the combination of various atoms which are combined by chemical bonds into a chain or network through a process called polymerization, resulting in polymers. So again, here's good and bad, right? Good, plastics are great for preserving food. They're used everywhere in our society. They're parts of cars, parts of houses, all kinds of stuff. But on the other hand, there's a problem with plastic waste, especially in the ocean. Okay, batteries. And once again, disposal of batteries can be an issue. They're made up of one or more electrochemical cells, and they store chemical energy to be converted at a later time into electrical energy. And we're now seeing them in cars, right? Tesla, Ford, Chevys, they're all putting huge batteries in cars to drive them. Again, good and bad. Fuel cells, they're devices that convert the chemical energy from fuel into electricity through a chemical reaction with an oxidizing agent. And finally, sodium bicarbonate, also known as baking soda, that's used to help different baked goods rise when in the oven. This happens due to a chemical reaction that produces carbon dioxide. Where do we see physics in daily life, or at least things that have been created by physics principles and then engineering? Communications, talked about that earlier. They've been revolutionized by the use of transistors and then lasers. Lasers are the backbone of your fiber optic signals. Electromagnetic waves are used in wireless devices, your cell phone. Lasers are used in medicine in place of cutting by surgical knives. GPS satellites provide accurate maps and recommended routes for travel. Very fast trains, made possible by magnetic levitation, which will reduce their friction with the track. X-rays and magnetic resonance imaging, MRIs, allow doctors to see within the body to make diagnoses without cutting the body up. Gamma rays, which you typically view as horrible and dangerous, and they are, but they're also used in measured amounts to kill cancerous cells in the body. The electric power grid, the whole thing is built on power generation, electromagnetic induction, AC circuits, and transformers, and so much physics and so much engineering.